Yes, hello Bess and BFST, you're welcome to another session, and this time we are testing for the difference between two variances. In the previous lecture we looked at how to test for the difference between two means for either small sample or large samples, and now we are only going to concentrate on testing the difference between two variances. And like for the mean of a large sample, of a small sample, still here we are going to be using the F-test. So if we have two independent samples from which two normally distributed populations in which variances are equal, and if these variances are compared, the sampling distribution of the variance is what we call an F distribution. So an F distribution can never be negative because here we are looking at variances, and remember variances are square numbers that are always positive. We can't have a square number that is negative, and an F distribution is positively skewed as the normal distribution was symmetrical. This is skewed, and then the mean of the value of F is approximately equal to 1. Remember, the one for a normal distribution is 0. And then the F distribution is also a family of curves based on the degrees of freedom, like the T distribution and the chi-square test. And now this is the formula for the F test. I remember you saw this in the previous topic and you were wondering how it came out. So if you want to get an F test when testing variances, we divide the variance, or we look at a population with a bigger variance and then divide it with the variance of a population that has a smaller variance. So this is what it means, that the larger of the two variances is the numerator, regardless of the sample sizes or the subscripts. Then the F-test has two terms for the degrees of freedom. That is the numerator and then the denominator. So N1 is always the larger sample size where the variance was obtained. So when finding the F-test value, the larger of the variance is the numerator of the formula, and then the smaller of the variance is always the denominator, and this is regardless of the sample size, like I've mentioned. So an F distribution, unlike other distributions, has various tables. So for example, when alpha is 0.05, the table is independent from when alpha is equal to 0.01, 0.025, 0.05, and 0.1. So I've put a sample of some, but I'll upload all of them and you'll be able to access them in the system. So you look at the level of alpha on top. So that is should always guide on which table or on which F table to use. So, and for a two-tailed test, we always divide alpha by 2. So if we are working at alpha is equal to 0.05, but then the scenario is two-tailed. For example, if we are looking at differences in the mean, maybe if we are looking at means of variances being different, then we divide 0.05 by 2, and therefore we consider the appropriate table, not necessarily the 0.05 table. So we have an example here that a medical researcher wishes to see whether the variance of the heart rates of smokers is different from the variance of heart rates of people who do not smoke. Two samples are selected and the data as shown below. So using alpha is equal to 0.5 is near enough evidence to support this claim. The researcher is wishing to see whether the variance of the heart rates of smokers is different. So meaning this is a two-tail because we are looking at the heart rates not being the same. So they can either be higher or lower. So at alpha is equal to 0.5, we shall consider alpha over 2, which will be 0.05 divided by 2, which will give us 0.025. So that should be the first thing we have in mind. So we are looking at, for smokers, the sample size was 26, and the variance was 36, and for non-smokers the sample size was 18 and the variance was 10. Step 1, we should always identify the hypothesis, and that means identifying the null and alternative hypothesis. And since we are comparing variances, so our null will be that the variances are equal, and therefore the alternative will be that the variances are not equal. So step 2, we look for the critical value. So now for the critical value, we are going to use the different degrees of freedom. So we are using alpha is equal to 0.025 because it is the half of 0.05. We are dividing alpha over 2 because it is a two-tailed. Whenever we have a not equal sign, we use the alpha over 2, or we divide alpha by 2. So that means we are dealing with a two-tailed scenario. So here we have the degrees of freedom of the numerator. Remember, the numerator is always that with a larger variance, regardless of the size of the sample size. So therefore, our degrees of freedom of the numerator. So what has a bigger variance? 10 and 36. So 36 is larger. So therefore, our N1 will be 26, and our degrees of freedom, or this will be our numerator, and our degrees of freedom for N1 will be, or for the numerator will be 26 minus 1, which will be 25. And the denominator, the other variance has been, sorry, the sample size has been 18, and therefore our degrees of freedom of the denominator will be 17. So we now go to the table. We've seen that the F table, so we are considering the 0.025 alpha table. So the 0.025 is here. So the columns represent the degrees of freedom, numerator, and these are columns, and then the rows down represent the degrees of freedom of the denominator. So you might realize that we might not have each sample size, but you always choose what is closest to the degrees of freedom. You might not have the exact number, so you always use what is closest to what you've got as your degrees of freedom for either numerator or denominator. So our numerator was 25, and we don't have a 25, but we have a 24. And then our denominator was 17. We have a 17 here. So what corresponds to 17 and 24? Is it 2.56? I think. So therefore our critical value will be 2.56. So now we look for the test value. Remember, our test value is variance of the numerator over variance of the denominator, and the numerator is always that larger variance, and the denominator is the smaller variance. So our F test, or our F value, will be 3.6. So now we make a decision. Does 3.6 lie in the critical region? Is it larger than the critical value? I think yes, 3.6 is greater than 2.56, meaning it is in the tail, it is in the critical region. So therefore, we reject the null hypothesis. And therefore, since the null hypothesis stated that the variances are the same, or the heartbeats will be the same, we reject it, and therefore there is enough evidence to support the claim that the variance of the heart rates of smokers and non-smokers are different. Thank you so much. I hope this has thrown more light to the previous lecture as well, because in the last subsection we looked at how at two process where we had to first find whether the variances were equal, and if not, that guided on which t-test formula to use. So thank you so much. Please stay safe.